Welcome to the Walton Pie. Today we're going to be talking about partial fraction decomposition, what it is, and how we are able to go ahead and use it. So the idea of partial fractions is that sometimes we might have a fraction that has a polynomial on the top and a polynomial on the bottom. And we can rewrite that fraction as the sum of fractions, assuming that we are able to factor the polynomial on the bottom into simpler polynomials. So the process is to first factor the denominator of the fraction as much as possible. So break it up into linear terms and quadratic terms. That is as simple as you are able to break up anything. If you have a cubic, it does break down into a linear term multiplied by a quadratic. However, sometimes those linear terms and those quadratic terms are complicated, and so if at all possible, break it down into as simple of a fraction as you can. In other words, break down the denominator into as simple of polynomials as possible. So once we've done that, we can then rewrite the fraction as the sum of several fractions, each one with one of the factors of the original denominator as the new denominator of that fraction. So an important thing that we have to remember though, before we start doing partial fraction decomposition, is to remember that it has to be a proper rational function. That means that the denominator must be a higher power of x, or whatever variable you have, than the numerator. So if it's not a proper rational function, we have to do polynomial division first in order to get a proper rational function. So in other words, if the numerator is the same degree as the denominator, or the numerator is a higher degree than the denominator, we first have to do polynomial division before we attempt partial fraction decomposition. So for example, let's say that we are trying to rewrite this fraction, x cubed minus 7x squared plus 2x minus 5 all over x minus 7, x plus 6 squared, x squared plus 1, 2x plus 3. Let's say we are trying to break this down. The way we would do this is we look at the denominator and we see, oh, it can be broken up into 4 different terms. We have an x minus 7, we have x plus 6 squared, we have x squared plus 1, and we have 2x plus 3. For each of these terms, because this is a proper rational function, we can then rewrite this where we put where we can fill in the numerator, and the numerator is always 1 degree smaller than the denominator. So for x minus 7, that is a degree 1 polynomial, meaning we have an x to the 1, that's our highest power of x in the bottom. So the top is going to have a degree 0 polynomial. So we are going to have x to the zeros, which in other words are constants. So the top of x minus 7 is just some unknown constant a. X plus 6 squared, that is a quadratic. So that is x squared is our highest power. So that means the numerator is going to have an x to the 1. So we are going to write that as a bx plus c. X squared plus 1, that's another quadratic. So the top is going to be a dx plus e, and then the 2x plus 3, that is a linear quadratic, or a linear polynomial, not a quadratic, sorry. That's a linear polynomial, so the top is going to be a constant. Now, something that you might see in other books, depending on how they approach partial fraction decomposition, is when we have something where we have a repeated root. In other words, this situation where we have x plus 6 all squared, they break that up as an x plus 6 and an x plus 6 squared term, and then those are just going to be constants on the top, because the base term, so the simplest way we could write the term is x plus 6, that's a linear term, so linear has constants on the top, and then you just have one different fraction for each power of that. So if it had been x plus 6 cubed, we would have a constant over x plus 6, a constant over x plus 6 squared, and another constant over x plus 6 cubed. Or you could write it similar to how we have in the first line, and you would have a quadratic over x plus 6 all cubed. Both ways are valid ways to approach this. This last method, though, comes in handy when you are dealing with certain methods for solving for the constants. However, both the first way written and the second way written are both valid ways to approach this problem. So once we've broken up our fraction into several simpler fractions, what we now need to do is we need to solve for the coefficients in the numerators. Like, we can't leave it at this where we say, oh, it's equal to a over x minus 7. We need to know what a is. Like, there is a very specific constant value that a takes, and we need to solve for that. And so there's a few different ways that we are able to solve for these constants. The first way is just a brute force method to be able to find the coefficients. And the way that we're going to do that is we are going to basically create a system of equations and solve them. If you're familiar with linear algebra, you can do this by converting the system of equations into an augmented matrix and doing row reduction. However, since these videos are designed for people who have not yet taken linear algebra, I will simply show that and then move on to the way that we can do it without needing to understand matrices. And so if you're not familiar with linear algebra, don't worry, we're going to go through it in a way that you don't need to know linear algebra to do. So let's go through an example of substitution. So let's say that we have 19x cubed minus 42x squared plus 74x minus 27 all over x minus 2 squared, x squared plus 1, x plus 5. First, we need to check, is this a proper rational function? The top is a cubic, and the bottom we have a quadratic times a linear, so that's an x to the 5th, essentially. So this is a proper rational function. And so breaking this down into our decomposition, we have an a over x minus 2, a b over x minus 2 squared, a cx plus d over x squared plus 1, and an e over x plus 5. Notice that I broke this down using the second method that we were doing back here. I broke this down using the very last line written on this page. There is another way that we could have written this, where we had this as a ax plus b over x minus 2 squared. However, those a's and these a's and that b and this b would be different. So we are going to break it down using this method. So the first way we are going to do this is we are going to just multiply everything by the entire denominator of our fraction. So we're going to multiply everything by x minus 2 squared, x squared plus 1, and x plus 5. Once we've done that, we get this. 19x cubed minus 42x squared plus 74x minus 27 is equal to this big mess of things. Now, all I did was I multiplied everything through and then I canceled out any terms that would have canceled. For example, the e over x plus 5 multiplied by the entire denominator is going to be e times the entire denominator except for the x plus 5 because that term canceled. The next thing we can do is we can expand out all of these polynomials, and this is messy, but it is one of the things that we're going to have to do if we do this method. So expanding out all of those polynomials, we get a times x to the 4th plus 3x cubed minus 9x squared plus 3x minus 10, and so on. And so once we've done that, we are now going to clump the terms together according to the power of x. So we are going to have x to the 4th times a plus c plus e, because in here, in our a term, we had an x to the 4th, but then we did not in our b, but we did in c and we did in e. So that's why we are getting x to the 4th times a plus c plus e. X cubed, we have a 3a, because in a we had a 3x cubed, and so on. So we are clumping them together according to the power of x. So we have x to the 4ths, we have x cubes, we have x squareds, we have x's, and we have the constants. Once we've clumped them all together that way, we are able to use that to set up our system of equations. So we are going to look at the powers of x. So this first line is our x to the 4ths. In this, on our 19x cubed minus 42x squared plus 74x minus 27, there aren't any x to the 4ths. So that's why we get a 0. And then on the other side we had a plus c plus e, because we had an a plus c plus e in our x to the 4th. And so just going through and clumping them all together, we have our first line is our x to the 4ths, then x cubes, x squareds, x's, and constants. And those are just pulling those terms directly from this. Once we have this, this is going to be our system of equations. Now, if you're familiar with linear algebra, we are able to write this as a system of equations that would look like this, where the first column corresponds to A, second column corresponds to B, and so on. And you would be able to row reduce this until you get it into row echelon form, and then that would be able to help you solve for A, B, C, D, and E. However, since most of you have not seen linear algebra, we are going to now do this by substitution. So the first step in substitution is to solve for one variable in terms of the others. So we're going to use the first equation and solve for A. So we find that A is equal to negative C minus E. So we just subtracted the C and the E over to the other side, and then what we are going to do is we substituted that into the other equations. So once we know that A is negative C minus E, for example in the second line, we can replace the 3A with 3 times negative C minus E, and that is going to give us 19 equals B minus 2C, because we originally had a plus C, but now we have a minus 3C. So we have taken A equals minus C minus E and plugged that in everywhere else that A showed up. Now in our next 4 lines, we are going to now try and solve for another variable in terms of the others. So now, using the second equation, we can solve for B and substitute that into everything else. So we find that B is 19 plus 2C minus D plus 7E, and we can plug that in everywhere else there was a B. So this time I wrote it out without simplifying everything first, and so we can see our third line had a 5 times B. Now it has a 5 times 19 plus 2C minus D plus 7E. And we are going to just do that everywhere that a B showed up, and once we've simplified and combined terms, it turns into something like this. Now our next goal is to try and find a way to be able to solve for another variable. And looking at the third and fifth equations, notice that they are pretty similar. They both have a 49e and they both have a constant of 95. So we are going to subtract the third equation from the fifth equation, and that's going to give us this. So 15 is 17c plus 19d. That is much simpler to deal with. So let's use that to solve for c. So c is going to be 15 minus 19d all over 17, and now we are going to plug that in to our fourth equation to write that in for c. Notice I'm not replacing it into the fifth equation because I'm hoping the fourth equation will give me a nice number. And it will, because we only now have d's in our fourth equation. So we can actually solve for what is d, then what is c, and we can replace those numbers in for our last equation rather than plugging in this nasty fraction. So plugging that in and simplifying gives us 55 is 285 17ths minus 650 17ths times d. So let's solve for d. So first multiplying everything by the 17 is going to give us 935 is 285 minus 650d. So 650 is negative 650d, so d is negative 1. We now have a number for one of our variables. So we can plug that in to our third equation to solve for c, and we can also replace all other d's with negative 1. So in our last equation, the plus 15d, that became a minus 15, and plugging negative 1 in everywhere there was a d, we are then able to find that c is 2, and then we can plug that in everywhere that there was a c, and we can combine a bunch of terms and simplify. And so now we can try and solve for some of the other ones. So our very last equation, we can solve for e. So negative 147 is 49e, so e is negative 3. And now we can plug that in everywhere else there was an e, and we are able to find all of the constants. A is 1, B is 3, C is 2, D is negative 1, and E is negative 3. We can now take all of those and replace those here. And so this is our partial fraction. This is our partial fraction decomposition of this nasty fraction. We were able to break this down and solve for the different constants by multiplying everything by the denominator and then using substitution to solve for the constants. Now, I'm sure a lot of you are thinking that took forever. Like, there's got to be some shortcuts. And there is. And this shortcut is called Heavysides Method. You might learn about it in class, and your teacher might refer to it as the cover-up method. Now, the reason that I didn't start with this method is this method will not always work. This method will work if you are solving for the constant in the numerator of a fraction where the denominator is a linear term. So back here, Heavysides method will be able to help us solve for the negative 3 over x plus 5. It won't help us solve for the other terms, because the x squared plus 1, that's not a linear term. And then the x minus 2 squared, well, we'll be able to solve for that one, but we won't be able to solve for the 1 over x minus 2, because there's an x minus 2 squared term. So Heavysides method has some limitations, but it is helpful to be able to shorten the process of the substitution. So let's use Heavysides method to find the same constants. So let's go and solve for e. We're able to solve for e and b because those are the constants in the numerator of a fraction where the denominator is a linear function, but specifically a linear function raised to the highest power it shows up. So because we have an x minus 2 squared, we can solve for b, but not a. So let's go and solve all of these. So the first step, if we are solving for e, is to multiply everything by x plus 5, everything by the denominator of e. So once we've done that, we can cancel out the x plus 5's here, and we are left with this. So at this point, we are basically saying, well, great, what are we supposed to do here? Well, the nice thing is we have an x plus 5 in a bunch of the terms still. So let's plug in x equals negative 5. The reason we can do this is these constants, this equation is true no matter what value x takes. So let's plug in an x value that makes a lot of the terms go to 0. So if we plug in x equals negative 5, a whole bunch of the stuff is just going to go to 0. And so by plugging in negative 5, we are able to get this fraction, so we quickly find that e is negative 3, which is the exact same thing that we found here. So the way that we are able to say this is the cover-up method is one way to calculate e is to cover up a bunch of stuff and evaluate. So because we are solving for e, we first are going to cover up any instance of x plus 5 in a denominator. So that's going to show up there and there. So those two are going to be covered up. And then we are then going to ignore any fraction that did not have an x plus 5 in the denominator. So all of those fractions with the line through them are going to be 0. We can then evaluate everything when x is negative 5, or in other words, when the denominator of the fraction with e would have been 0. So that's going to mean that we can then plug in negative 5 everywhere in that we have an x that was not crossed out or ignored, and then we are able to quickly jump straight to e. And so that's why this is this has the nickname of the cover-up method. We can also use it to solve for b. So we are going to go through and do the multiplication version first, and then we are going to cover up terms and show the cover-up version of this same method. So first, multiply everything by the denominator of b, which is x minus 2 squared, and then we are going to be able to cancel out quite a bit of stuff. Notice that with our a over x minus 2 term, part of the numerator got canceled out. So the x minus 2 squared over x minus 2 now just becomes an x minus 2 in the numerator. So once we've simplified a little bit, we can then evaluate everything when x minus 2 squared is 0, or in other words, when x equals 2. So a whole bunch of stuff is going to go to 0, and we are able to evaluate this and see that b is equal to 3. However, Heavysides method can only get us to the point where we can solve for b and e in our example. Once you have those two values, the system of equations does become much simpler, as there would only be 3 unknown constants. However, there is a generalization of Heavysides method that will allow us to solve for the constants on top of fractions with a repeated linear term in the denominator. So this method could be used in situations like this, where we had an a times x minus 2. We would be able to use this method to be able to solve for what a would be. The way we solve for a is we then take the derivative of the entire equation once we've gotten to this point. So taking the derivative of everything with respect to x is this pretty thing. Now the nice thing is if we then if after we've taken one derivative then we plug in x equals 2, we are able to get a whole bunch of stuff that goes to 0, and we are left with this, because all of that is crossed out went to 0, and then the other fraction on the other side went to 1. And so that gave us that a was 1. Now, this method works to find some of the constants that Heavysides method failed to find, but the method gets pretty messy. So I would not actually recommend using this all the time. However, some fractions would be pretty straightforward. So for example, if we were back here, and our original fraction had a constant on the top as opposed to 19x cubed minus 42x squared plus 74x minus 27, if that was a constant, the derivative would have been a lot easier. We would have had a whole bunch of stuff that would have canceled instead of this messy 137x to the fourth plus whatever. Like, that's a pretty messy fraction to try and evaluate, but it is doable. And so if the fraction was a little bit easier, then this method might be a little bit easier. However, I would usually stick to doing the substitution method rather than trying to use these derivatives. However, this is a method that is going to work. Now, I did promise I would show how to solve for b using the cover-up technique, and we got a little bit sidetracked with the other method that we could do to have also solved for a at the same time. But using the cover-up technique, we're going to first want to cover up any instance of x minus 2 squared in the denominator. So those two spots are going to just disappear. The next thing we want to do is to set all fractions which don't have an x minus 2 squared in the denominator to 0. Notice that this is also going to set a to be 0. Next, we're going to evaluate everything when x is equal to 2, because that is when x minus 2 is equal to 0. So once we've done that, we get 19 times 8 minus 42 times 4 plus 74 times 2 minus 27 all over 5 times 7, which is 105 over 35, which gives us 3. So that tells us that b is going to be 3. And that's how we're able to solve for b using the cover-up method. I hope this video was very helpful in understanding the partial fraction decomposition method. I hope that if it was helpful, that you will consider liking and subscribing so that I can continue to make these videos. If not, I'm glad that you were able to watch it and enjoy, and I hope to see you again soon. Have a great rest of your day, and good luck with the rest of your math.